Hello everyone, welcome back to the PyroMath YouTube channel. Today we'll be going over some AIME level geometry topics. Specifically, we'll be studying the law of sines and how to use that to derive the ratio lemma. For many of you preparing for the AIME, ARML, HMMT, and other such competitions, this should not be such an unfamiliar topic. Yet rather than just applying the law of sines, many questions require the proof of law of sines in a way such that parts of the proof are crucial to solve the problem. So in this lecture, not only will we be presenting the formulas themselves, also their derivations and a problem in which they are used. So enjoy. Alright then, let's get started. So we'll start off with the law of sines, and I have written it right here. Basically, what the law of sines is saying is in this configuration above, we have that a divided by sine a. In the diagram, I have represented it as alpha, but generally it's known as angle A. Anyway, a divided by sine a equals b divided by sine b equals c divided by sine c equals 2r. I've not shown r in this diagram, but we'll see that moving forward with the proof of it. Oops. Let's move that down for later. Alright, so let's start with the proof of the law of sines. Let's talk about triangle ABC and the circle that circumscribes it. Note that I have not proved yet that a circle circumscribes a triangle, but that's needed for this proof. Okay, and another thing we need to know is the inscribed angle theorem. Basically, what that's saying is if there's a circle, my very beautiful circle, and there is a angle that inscribes an arc of the circle, that is this arc. This angle is constant for any angle that inscribes that same arc. Also, this is basically what the theorem is saying, but what we can also do with the theorem is that if we have the center of the circle, then this angle is actually 2 times this angle. So we're going to need that for the proof. And let's get this out of the way. Alright, so if we have angle theta here, in the previous example I called it A, let's just call it theta, because normally when you have one angle that's just customary to call it that, then we have that from the inscribed angle theorem, angle BOC is 2 times theta. And note that BOC is actually a isosceles triangle because both BO and OC are both R. R is the radius of the circumcircle of ABC. And since it's isosceles, then we have that the angle bisector is also the altitude. So drawing the altitude from O to BC, we actually split the angle, and it actually splits BC in half because it's also the perpendicular bisector. Alright, so if we're splitting BC in half, note that BC equals A. This is another convention. That looks like an alpha, but anyway, BC equals A. The angle big A, this one, is always opposite of the side little a. Okay, moving forward, how can we represent A or A halves in terms of theta? Well, using basic trigonometry, we know that opposite over hypotenuse is the sine. So A over 2 divided by R equals sine theta. So note that A equals 2R sine theta. All I have done here is multiply out the denominators. Okay, nice. So this gives, and then actually you have to divide by sine theta. So we get A divided by sine theta equals 2R. Okay, So doing a similar thing with all of A, B, C gives us that they are all equal to 2R. So what this means is since they're all equal to 2R, they're equal to each other. And therefore, looking back, we have what we wanted. A over sine A equals B over sine B equals C over sine C equals 2 times R. All right. Now that that's clear, let's let's move on. Oops, I hinted at the problem that we'll be doing later. Anyway, let's do a lemma. This is known as the ratio lemma that is actually an application of the law of sines. Basically, we have a configuration where we have triangle ABC and point D on BC. And we have that this is theta 1, this is theta 2, and we have the relation that BD divided by DC equals AB divided by AC times the sine of theta 1 divided by the sine of theta 2. So looking at the sines, we already see that the law of sines could be useful. And let's explore that idea a little more deeply. So we have that by the law of sines on triangle ABD, we have that BD divided by sine theta 1. Okay, already we're seeing the BD and the sine theta 1, and so we know we're kind of on the right track. Anyway, moving on, then we have that AB equals, okay, before we move on, I'm going to define that angle ADB as alpha for simplicity. So we have that AB divided by sine alpha. Okay, nice. And similarly with triangle ADC, we can do, let's move over a little bit. Okay, apologies that we cannot see the diagram anymore, but moving forward, DC divided by sine theta 2. If you need to see the diagram, you can go back in the video. Equals AC divided by sine. Okay. So here, notice that we have that ADB is alpha, and now we want to use ADC. And remember that ADC is supplementary to ADB, meaning that the measure of ADC is 180 minus alpha. Okay, so we got that DC divided by sine theta 1 equals AC divided by sine 180 minus alpha. Okay, an important property of sine is sine alpha, or sine anything, equals sine 180 minus alpha. Okay, so we can actually cancel that out and call it sine alpha. And so from the two equations, let's put them side to side. This one and this one, we see that sine alpha is constant. And so that should get us thinking that maybe we should solve both equations for sine alpha and then set it equal. So let's do that. Okay, so the first one, we get that, let's go back for a second. Yep. All right. We get AB sine theta 1 divided by BD equals alpha. And I'm not going to write alpha because we also know that, I mean sine alpha, because We can solve sine alpha in the second equation and also get AC by sine theta 2 divided by GC, because both of them equal sine alpha, solving the two equations. And now all we do is rearrange, and we get AB divided by AC, dividing AC by both sides, and then times sine theta 1 divided by sine theta 2, dividing sine theta 2 by both sides, and then multiplying BD on both sides, BD divided by DC. Okay, is this what we wanted? Yes, it is. Okay, nice. And another note I would like to put in here is this is the generalization of something many of you might know called the angle bisector theorem. Basically, we know that angle bisector splits an angle in half. So in this case, if AD was the angle bisector, then we would have theta 1 equals theta 2, meaning that sine theta 1 equals sine theta 2. And then this term right here would disappear because sine theta 1 equals sine theta 2, meaning that sine theta 1 divided by sine theta 2 equals 1. And so then we have just this result as the angle bisector theorem. But I think knowing the ratio lemma is also important because many times the angle bisector itself doesn't show up, and other kinds of, well, we call it AD from before, a cevian, and other types of cevians show up, and it's nice knowing angles in relation with sides. All right, let's move on to the question relating to today's lecture. This question was posed by AoPS user tan theta 67. Thank you. All right, so in triangle ABC, let P and Q be the radii of the two circles passing through A and touching BC. All right, at B and C, prove that PQ equals R squared using the extended law of sines. So in this problem, he gave us that we need to use the extended law of sines, but I mean, that's what we kind of focused on today. So probably should have been evident anyway. All right, so I've drawn a picture for us right here. And so we have triangle ABC and two triangles with radii P and Q. I haven't put that in the picture, but this is P and this is Q. All right, now we need to prove that PQ equals R squared using the extended law of sines. So capital R is normally used for the circumradius of a triangle ABC, and that's the same R that we saw before in the extended law of sines. So let's just get to it. One thing we need to know for this problem is that is called the tangent theorem. Basically what we have is if we have a tangent, or I'm just going to draw this differently. If we have a circle and a tangent meaning it intersects at one point, and this is 90 degrees. That's okay. We don't need that for this. Basically, this theorem states that this angle is equal to any other angle that's circumscribed by the circle that inscribes that arc, meaning any angle like that has the same length as, has the same measure, I should say, as that angle. Basically, what that tells us is in this picture, oops, what happened there? Any angle like that, imagine that touches, the measure of that is equal to this angle. And remember by the inscribed angle theorem that the angle having the center AEB is half of that, or sorry, it's 2 times of that. So if we have angle ABC as beta, then we have that angle AEB equals 2 beta. And if you recall the proof of the law of sines, we have that B, let me move over a bit. Let's move down, I guess. We have that BA is equal to 2 times the radius of the circle with center E. This one is P, remember? 2 times P sine of beta. Well, why is this? Remember oops, that beta is terrible. Why is this? Remember how we proved the law of sines? We dropped a perpendicular from the center, and then we just used basic trigonometry. Okay, we can literally do the same thing on the other side. Draw perpendicular, same logic, and we get that AC equals 2 times Q sine of C. Okay, so now we solve for P and Q. So we get that BA divided by 2 sine of B. Or sorry, beta, my bad. You know what, let's just call it B, because we called the other one C. Now that'll make it confusing. Anyway, AC divided by 2 sine of C. Okay, so this equals P and this equals Q. All I did was divide out and solve for P and Q. Okay, now we want to prove that PQ is equals R squared, remembered. So we have that PQ equals BA times AC divided by 4 sine of B sine of C. Oops. Okay, so here is where we actually use the extended law of sines. So the extended law of sines is just basically the law of sines, but with the 2R part. The main law of sines is just with the A over the sine A equals B over sine B, but including the 2R, we call it the extended law of sines. It doesn't really matter, but till now we just kind of use part of the proof of that. And that's how usually problems are. You use parts of proofs of famous theorems and lemmas and stuff. But here we're actually going to plug it in. Let's go back to the diagram. Remember that by the law of sines, or the extended law of sines, AB divided by sine of C, this angle, equals 2R. Similarly, AC divided by the sine of B equals 2R. So BA divided by the sine of C equals 2R, and AC divided by the sine of B equals 2R. So if we factor the 1/4 out, we can factor this as okay, there we go. And as I just said, each of them are equal to 2R. And therefore, this equals R squared. There we go. Okay, that was a nice problem. So basically what we did here was we solved for P and Q using angles, basic angles, and the proof of the law of sines. Then we just found it in terms of P and Q, BA and AC, and some angles. Then we just multiplied it. We refactored it so that we can actually apply the extended law of sines. And at the end, we ended up with a clear R squared. Before we finish off today's lecture, I would like to give a few final tips involving using the law of sines and the ratio lemma and how to apply them in the real world situations. So, if a problem involves many sides, angles, and overall gives off a bashy sense, law of sines could be useful. This is because if it gives off a bashy sense, then we know that it's a computational geometry problem, and law of sines is very important in computational geometry, so we have that result. And when ratios are brought up in relation with sides, angles, and cevians, it is useful to consider the applications of both the law of sines and ratio lemma, as the ratio lemma deals with ratios. I mean, that's how we get that. If a circumradius appears in a problem, thinking of law of sines should be on the list of ideas to explore. This is because there's not a lot of ideas or principles that relate to circumradii and triangles and all that kind of stuff. And more than likely, law of sines will be useful. I hope you enjoyed today's lecture and the problem that we presented. We hope to see you in other lectures. Thank you.